understand from recent conversations is that exam 4 is next Friday. Oh, there we go. Exam 4, that would be the 19th. And the topics will be everything up through stresses and beams. And there's still one more thing that we have to talk about with stresses and beams. So back to stresses and beams. Does anyone have any homework questions? I haven't assigned much homework recently. But, okay, so today we're going to finish this topic. Yes. Oh, there's one more thing that, I mean, you can calculate this, but I just want to point something out. So for the stress due to shear force, we know that tau xy is equal to negative VQ over IB. And there are two cross-sectional shapes. The first one is rectangular. And you get better results if it's taller than it is wide. And we can do that for any location on the cross-section. And then the second one is circular. But this one, we can only calculate the stress due to shear force at the neutral axis. And since we can only calculate that at along one line on the cross section, there's only one possible value for the Q that we're calculating. Because remember, the definition of Q, if this is the neutral axis, okay, and that also is our, this is the neutral axis and the line of interest. And that means that this is the area. That means that the centroid has to be here. And that means that this has to be D. So Q is just equal to well, let's figure this stuff out. So A is the shaded region area is always pi r squared over 2. And the distance from the base of a semicircle to the centroid of a semicircle is 4r over 3 pi. And so Q is always equal to a times d, so that's pi r squared over 2 times 4r over 3 pi. We get some cancellations, and you get a q value of pi does not cancel with a square exponent. Pi, so what's this thing? Pi, r squared. Pi cancels with pi. Okay, so we have 2r to the third over 3. That's the only q that can ever be relevant for us for a circular cross section, just because we can't move our line of interest anywhere else. Well, since the only centroids we need for this are rectangles, probably, and then semicircles, and I'll probably just give you the formula for Q. Okay, so now the total stress tensor is equal to the stress tensor due to tension compression plus the stress tensor due to bending moment plus the stress tensor due to the shear force plus the stress tensor due to the torque. And this is the last one. We haven't done that yet. Okay, so first, let's think about what what element of torque we expect to be affected. So let's think about a beam with a circular cross section to start with. Okay, there's the coordinate system we're using. And let's imagine that we put this in a positive torque, and that means that we have a positive couple in the direction of the x-axis, you know, a couple in the direction of the positive x-axis on the right side, and in the negative x direction on the left side. And let's think about what this would do to stress elements on the surface. So if we start out with a stress element like this, just imagine like we start out with sort of a rectangular piece on the surface of that. I have it sort of curved because I'm drawing it with a finite size, but imagine limiting this down to 0 size. What's going to be the deformation of that thing when you apply this torque? So this torque causes a rotation of that side that way relative to this. Yep, and so it's going to twist. We can think of the twisting that would happen as going like this. right? And in order to get it to twist like that, yeah, it's an angle. And so you can see that it's going to be a shear stress. That's going to require a force pushing that side down and a force pushing this side up. Okay. So if you think of that as a stress element, what are those? I guess they're really tractions. Like what face is it on? The positive and negative, what face? X face. And what direction? Y direction. Yep. In this case, so you see that a positive internal torque is going to lead to a negative XY shear stress. Okay. So a positive internal torque leads to a negative tau XY. Tell me if you can visualize this. Might be a little too, without drawing more pictures, this might be a little too complicated. You have a question before I do this, Brian?
Oh, no, I was trying to.
Okay. So now, though, here's, so now imagine that I take this orange thing and put it up on the top. Can you picture what would happen to that stress cube? Then it's going to be on the, it's still going to be on the X face, but it's going to be in the Z direction, right? So, in other words, this relationship only holds for a stress element that's on the positive Z side of the surface, okay? So this is on the surface in the direction of positive Z from the centroid. Okay. So a positive torque means,
It'll still be counterclockwise.
yeah, if you're looking down this way, it's counterclockwise. When you start talking about any kind of 3D stuff, you have to be careful thinking clockwise and counterclockwise because it switches depending on which side you're looking from, you know? So, but yeah, the way it works now is if you're looking down the positive axis, positive is counterclockwise. Okay, so notice that this idea is a complexity that we didn't have with the stress due to the shear force. We didn't have to worry about where we were on the surface to think about what element. So that's going to be a big thing when we go. Okay. Yes.
That rectangle.
Mm-hmm. Mm-hmm. Yeah, that's right. I'm just saying these are the two forces you need to deform it in this. And so think about what stress element that is. This line over here on the right side of this little element is the X. That's the positive X face of that cube. You know, this is the x-axis.
Yeah, so that's the x-axis. But if you draw that arrow on the parallelogram, it would be like on the y.
Yes, it's in the negative y direction. But the face here, like, think of that orange thing as the front of a stress cube. Okay? The face that this force is acting on is the right side. That's the positive x face. So it's on the positive x face in the negative y direction. Well, it's both. Remember that for the materials we're dealing with, linear elastic isotropic materials, remember what the compliance matrix looks like. In the shear part of the compliance matrix, all you have is a constant relating the shear stress to the corresponding shear strain. So if you have one element of shear strain, that's also the element of shear stress you have. Okay. We can do this for two different cross-sectional shapes. So the beam requirements. First, we can do it for round cross-sections. Circular. And second, we can do it for thin-walled, closed tubes. And these can be any shape. This is all of a sudden a pretty amazing flexibility that we're going to have. But so you could have a cross section like this. I'm trying to draw all these thicknesses different. Those are both fine. The thing we can't do is well, okay, let me go back to, so let me just go back to a triangle shape. But the thing we can't do is this, because it's not a closed tube. Okay. And these are the cross sections. So this is no good. These two are okay. These are the cross sections we can deal with. Let's say less than 1/10 of the diameter. But again, like most of these things, the way it comes about when you're deriving these equations is that you limit it down to 0. So the thinner the tubes are, the better your answers are. And so there's no real cutoff, but let's say 1/10 of the. Yeah, right. I mean, you could do it that way, and but it's just if the hole was a little bigger, it would give you a little better results. A little bigger, a little bigger. There's no real like cutoff. It just has to do with what precision you'll accept. Um, and yes. Mhm. Uh-huh. Mhm. So first of all, remember that um, we just position these beams like horizontally just to visualize them and do the math and stuff. So it doesn't matter what, but you could have something like a thing like that with two handles attached, and for some reason there's going to be a force applied that way and a force applied that way. That would, and if this is makes a fixed joint with the ground, that would cause this torque along that. Mhm. Um, a lot of times motors, you know, that's what's causing this torque. Um, the motor's applying some force to something, and so, uh, there's some kind of shaft that's being torqued. Yep. or a thin-walled rectangle, a thin-walled tube rectangle. Um, yes, yep. Um, and we'll do a couple examples where we combine all this stuff. But yeah, so I guess I like that way of thinking. So yeah, what could we do like a full problem of and figure out everything on the whole cross section? We actually can't do it for a circular cross section. For a circular cross section, we can't figure out the stress due to the shear force unless we only want it along the neutral axis. Okay, so the only beam where we could calculate the stress over the entire cross section is a thin walled rectangular tube. So too bad. Uh, yeah, right. Um, yeah, that's a real shame. Yeah. Um, Although remember that in a lot of beam problems, there's no torque. Like a lot of times, torque will appear sort of separately in problems from the rest of the stuff. It's not as common that you have torque going on at the same time that you have transverse loads going on. So if so, I'm combining all these things together, but um, normally you either have like a beam problem or you have a torque problem. Okay, well, so first we're going to go to uh, cross sections. So the formula that we're going to use is that the torque and these subscripts, I'm going to write the subscripts X, Y, but I want you to notice I'm writing them uppercase. Uh, Normally I write them lowercase, and I'm doing that because of this complexity that I mentioned before, and it's going to sort of come back. We're going to have to deal with that. That which elements of the shear stress you're dealing with depend on where on the surface you are. Okay. But this torque, capital X, capital Y, is going to be equal to negative internal torque times rho. That's the distance from the centroid to the point of interest, divided by this new thing, I sub p. This I sub p is called the polar moment of inertia. And you can think of that rho as like a radius to the point that you care about. So before we can do these calculations, we have to define this I sub p. Oh, also that negative comes in just, like when I first drew the picture of this beam being torqued and drew the element that's being deformed. That negative comes about just like because of how we talked about it. Okay. A positive torque corresponds to a negative xy. This rho is a variable that's multiplied to it, and this p is a subscript. Okay, so polar moment of inertia. Um, the integral definition for this says I sub p is equal to the integral of rho squared dA, and this is from, you know, the inner radius to the outer radius. It looks a lot like the expression for the area moment of inertia. Anyone happen to remember that well enough to notice what the difference is here? There's only one difference. It's squared in the area moment of inertia too. Yes, that's the difference. In this case, we're talking about a radial distance from the centroid. Okay. And in the other case, we're talking about a vertical value of y from the neutral axis. So that one's all up and down. This one is radial. That's what makes this polar. So this rho is the distance from the centroid to this infinitesimal area dA. We only need this for a circular cross section. You can use this. It doesn't take very long, but I'm not going to do it, I don't think. But this formula gives you that I sub p is equal to pi times the radius to the fourth over 2 for a solid circular cross section. And for a hollow circular cross section, it's pi over 2 times the quantity r outer to the fourth minus r inner to the fourth.
All other tubular shapes that were circles, you have to go through the integral.
No, so we are not going to use the polar moment of inertia for the thin-walled tubes. We'll have a whole different way of calculating it. And now, so now we're back to this formula that says tau capital X capital Y is equal to negative torque times rho divided by I sub p. And the coordinate system, capital X, capital Y, capital Z, has the capital Z axis pointing from the centroid toward the point of interest. Okay, so as an example, let's say that we have this circular cross section and we want to calculate the stress due to torque here. How do we do that? Here's the centroid. Okay. So we're going to set up an initial coordinate system with the z-axis in that direction. The x-axis is still pointing out towards us. And the y-axis then has to be this direction. Okay. This is, when you first start thinking about this is sort of tricky. It'll make good sense, I think, to you and not too long. But now the coordinate system that we want in the end is this one, right? This is the lowercase one. Okay. So how do we do this? Well, we use the formula, and it gives us the torque in this capital coordinate system, right? And once we have that stress tensor, we use rotation matrices to transform the stress in this coordinate system to the stress in this coordinate system. Okay, so I've been coddling you guys for too long. Yeah, exactly. It's a big advantage when you know what you're writing. Okay. So the steps. 1, use the formula to calculate, I'll call it the stress tensor, capital XYZ. And then second, the stress tensor that we want is going to be Q times the stress XYZ, capital XYZ, I mean, times Q transpose. Yeah, that's right. All right, so if this, let's say the angle between this little y and big Z is like 30 degrees, what would be the rotation matrix that we would have to use? About what axis and what's the angle? Yes, very good. Yeah. So
surprised.
well, I just had to think. I wasn't that surprised. I was just like trying to think of so we're talking about a positive to get from this to this. It's a positive x rotation. Okay. And you have to go 30 degrees to make those line up, another 90 degrees to make those line up. So positive 120 about x. And so make that your Q matrix, do the transformation, and then finally you can add that stress tensor to the stress tensors you got from bending moment and all that stuff. All right. So let me do an example problem. Let's say we have a cantilever shaft connected on the left, and we have a torque of 40,000 Newton meters. And let's say that the cross section, so there's the centroid, there's our y-axis, there's our z-axis, the x-axis is coming out towards us. And let's say that we want to calculate the stress tensor at a point here, and we want to calculate the stress tensor at a point here. And actually, let's make this one to be halfway out, okay? Because these stresses, you have a stress at every one of these points in this cross section. So part A, what's the stress due to torque at A? Part B, what's the stress due to torque at B? Okay, so first we have to figure out what the internal torque is going to be at points inside there. That's a very easy internal loads problem, but remember that what we're dealing with are internal loads. So how many cuts do we have to make? Just one. We don't even, so this represents the whole beam. It doesn't affect the answer here, so okay, so I'll make a, before we do, I'm sorry, I'm gonna make your notes look bad. Before we do the cut, we have to calculate the external loads. So first I'll do a free body diagram of the whole thing. Okay, so we have, well, probably not, but I'm going to show you how you would. Okay, so 40,000 Newton torque, Newton meter torque there. And over here we have our reaction torque, TR. The moment equation about the x-axis says TR plus 40,000 is equal to 0. So that reaction torque is negative 40,000. And now that we have that, we can do our cut. So for points inside this shaft, we have a reaction torque going this way of 40,000, we figured out. And now we have our internal torque, T. So the moment equation about the x-axis says negative 40,000 plus T is equal to 0. So T is positive 40,000. Okay, so at every x value along this shaft, the internal torque is positive 40,000. So this is valid for every x. And now that we know that, we can calculate the polar moment of inertia. That's pi over 2. Did I give a radius for this? 0.05 meters, 5 centimeters. So the cross-sectional radius is 0.05 meters. So the polar moment of inertia is pi over 2 times 0.05 to the fourth. And that is 9.82 times 10 to the minus 6 meters to the fourth. And so this is the polar moment of inertia we're going to use for both A and B. That represents the whole cross section, okay? And so now I can split it up into parts A and B. For part A, the point that we're interested in is this. And so in this case, our capital coordinate system is equal to our normal coordinate system, our actual coordinate system. Okay. So tau xy is negative 40,000 times the distance from the centroid to the point of interest. In this case, that's just the radius. Divided by 9.82 times 10 to the minus 6. And you get a value of 2.04 times 10 to the 8th negative pascals. And our temporary coordinate system is already lined up with our actual coordinate system. We don't have to do any kind of rotation. So our stress tensor due to torque at this point is 0, negative 2.04 times 10 to the 8, 0, then negative 2.04 times 10 to the 8, and zeros everywhere else. Any questions about that? Yep.
So when we do add up our total sigma, we should have a full cube eventually.
Let's see, we still won't have YY or ZZ, but we can have everything else. And then for part B, so for this one now, here's the centroid. The point we want is halfway from the centroid to the end. And so our temporary coordinate system is this way. Our final coordinate system is this way. And so it's going to be 180-degree rotation about X. Our tau capital X capital Y is equal to negative 40,000 times rho. What's the distance rho from the centroid to the point of interest? Yep. 0.025 divided by 9.82 times 10 to the minus 6. And we just get half of what we got 1.02 times 10 to the 8th negative. And so our stress tensor in the temporary coordinate system is 0, negative 1.02 times 10 to the 8th, 0, negative 1.02 times 10 to the 8th, 0, 0, 0, 0, 0. A rotation matrix is 180 degrees about the x-axis, which is, so that's going to be 1, 0, 0, and then negative 1, 0, 0, negative 1. So our final stress tensor due to torque is equal to Q times the temporary stress tensor times Q transpose and in that case all you get is it just flips the signs of these two because of the 180 degrees. You can just plug it into your calculator. You don't have to see that, but pascals. What is the stress tensor due to torque? Okay, this is the last question, and then we're done. What's the stress tensor due to the torque for a point at the centroid? 0. That's right, because rho is 0, so none of the other stuff matters. Any questions?
You will.
Yeah.
But